Imagine standing on a quiet hillside, the night sky a blanket of stars, and then thinking that somewhere beyond that glittering tapestry lies an almost empty space so vast that it feels like a cosmic void. In the heart of the constellation Boötes, astronomers have found a region so devoid of galaxies that it is often called the Great Nothing. This silent expanse stretches nearly 200 million light-years across, a bubble in the cosmic fabric that challenges our ideas about how the universe is built. In this episode we will journey into that emptiness, uncover its secrets, and see why it matters to the story of everything in the cosmic void today. Voids are the vast, low-density pockets that punctuate the cosmic web. Picture the universe as a sprawling spiderweb, with galaxies and clusters forming the threads and knots, and the voids as the empty spaces between. These regions contain far fewer galaxies than the surrounding filaments, sometimes only a handful of stars in a volume that could hold thousands. They are not empty in the sense of being devoid of everything, they still contain dark matter, diffuse gas, and the faint glow of the cosmic microwave background. Yet the lack of luminous galaxies gives them the eerie character of a silent, almost invisible bubble in space today. The Boötes void, discovered in 1981, sits roughly 700 million light-years from Earth in the direction of the constellation Boötes. Its diameter is about 200 million light-years, making it one of the largest known voids. While a region of that size would normally contain around 2,000 galaxies, the Boötes void holds only about 60. This extreme underdensity means that the space inside is almost a vacuum, with galaxies sparsely scattered like islands in a vast ocean. The void's shape is roughly spherical, but its edges are not sharply defined. Instead, galaxies gradually thicken into the surrounding filaments that weave the cosmic web across the vast cosmic sea. In 1981, astronomer Robert Kirshner and his team were mapping the redshifts of galaxies to chart the large-scale structure of the universe. While compiling their data, they noticed an unexpected absence of galaxies in a particular patch of sky. The void was so pronounced that it earned the nickname Great Nothing, a playful nod to its emptiness. Kirshner's discovery was a watershed moment, revealing that the universe is not a uniform sea of matter but a complex tapestry of filaments, walls, and voids. It also opened a new frontier for studying how galaxies cluster and how the large-scale structure evolves over cosmic time. Within the Boötes void, the galaxy count is astonishingly low. Imagine a region the size of a continent, yet only 60 galaxies dot its expanse. In contrast, a typical patch of sky the same size would host thousands of galaxies, each a glittering city of stars. The scarcity of luminous matter creates a cosmic silence, a place where light from distant galaxies must travel through almost nothing before reaching us. This emptiness also means that gravitational forces are weaker, allowing the void to expand faster than its denser surroundings. The result is a bubble that grows, stretching the fabric of space itself in the silent void. The universe is stitched together by a vast network of filaments, long strands of galaxies and dark matter that connect clusters across millions of light-years. These filaments form the edges of voids, creating a cosmic web that resembles a spider's net. The Boötes void sits in the middle of this web, its spherical shape carved by the surrounding filaments that pull matter toward themselves. As galaxies move along these strands, they leave behind vast, empty pockets. The interplay between gravity and the expansion of space shapes the web, and the voids grow as matter flows away from them, leaving behind a silent, empty canvas that stretches across the cosmos in the silent void. Because a void contains less mass, its gravitational pull is weaker than that of surrounding filaments. This difference causes space inside the void to expand slightly faster than the rest of the universe. Think of it as a balloon that is being inflated more rapidly in one region than in another. Over billions of years, this differential expansion stretches the void, making it larger and emptier. Scientists use these differences to test models of dark energy, the mysterious force driving the accelerated expansion of the universe. The Boötes void, with its extreme emptiness, provides a natural laboratory for measuring how space itself behaves when it is almost devoid of matter in the silent void. At the periphery of the Boötes void lie the Hercules superclusters, massive conglomerations of galaxies that form the skeleton of the surrounding cosmic web. These superclusters are like the ribs of a giant organism, providing structural support and drawing matter toward themselves. The galaxies within the Hercules clusters are tightly bound, moving in a dance governed by gravity. Their gravitational pull creates a boundary that separates the void from the denser regions. Observations show that the void's edge is not a sharp line but a gradual transition where galaxy density rises. This boundary is crucial for understanding how matter migrates from voids into the filaments that weave the universe together in the silent void. Voids are born from the same processes that create galaxies, but in regions where matter is initially sparse. In the early universe, tiny quantum fluctuations grew into density variations. Over billions of years, gravity pulled matter into the denser peaks, forming galaxies and clusters. The opposite happened in the low-density troughs. With less material to attract, those regions expanded and became emptier. As galaxies congregated elsewhere, the voids grew larger, carving out the cosmic landscape. This cosmic dance of attraction and repulsion shapes the universe's large-scale structure, leaving behind vast, silent chambers that are the Boötes void and its kin in the silent void. Measuring a void is a subtle art because emptiness is harder to quantify than brightness. Astronomers rely on redshift surveys, mapping the distance and motion of thousands of galaxies to trace the three-dimensional skeleton of the cosmos. The Boötes void stands out as a region with an unusually low galaxy density, but confirming its size requires careful statistical analysis and deep imaging. Additionally, the faint glow of the cosmic microwave background threads through the void, offering a background against which to measure its influence on light. These challenges push the limits of current telescopes and data processing, driving innovations in survey techniques and computational modeling in the silent void. Voids like the Boötes void are not merely empty spaces, they are key to testing cosmological theories. Because the expansion rate inside a void differs from that of denser regions, scientists can use voids to probe the nature of dark energy and the geometry of the universe. The distribution and size of voids also provide clues about the initial conditions of the cosmos and the growth of structure over time. By studying the subtle distortions in the light that passes through a void, researchers can refine models of how gravity behaves on the largest scales. In this way, the great nothing becomes a laboratory for understanding the fundamental forces that shape everything in the silent void. As we look back at the vast, silent expanse of the Boötes void, we are reminded that the universe is a tapestry of extremes, dense clusters and empty voids woven together by gravity and expansion. The great nothing, though almost devoid of galaxies, tells a story of cosmic evolution, of how matter gathers and emptiness grows. It challenges our theories, sharpens our tools, and invites us to keep exploring the unseen. The next time you gaze at the night sky, consider that somewhere beyond the glittering stars lies a silent bubble, a cosmic laboratory waiting to reveal more secrets. If you enjoyed this story, subscribe for more real mysteries and discoveries in the silent void.